Our next example, we're going to talk about getting a fourth degree Taylor polynomial for e to the x. And we're going to center it again at x equals 0, so it's also a Maclaurin polynomial since it's centered at x equals 0. All right, so again, we're going to have the exact same form. It doesn't matter what function we're using. The polynomial always takes the same form. All right, we have, we're centering it at 0, so it's going to be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared times the third derivative at 0 over 3 factorial times x cubed, and so on. Right? Again, this is the fourth derivative of f at x equals 0 over 4 factorial and then x to the fourth. All right, so now I need the first, second, third, and fourth derivatives. E to the x is conveniently very easy. Nice derivatives. And also finding all of those at x equals 0, just as easy. E to the 0 is always 1. So we have all of our derivatives at x equals 0 are 1. So for e to the x, our fourth degree Taylor polynomial is going to look like this. We have f of 0 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. That's our fourth degree Taylor polynomial. If we wanted to generalize that to the nth Taylor polynomial, or in this case the nth Maclaurin polynomial, since it's centered at x equals 0, we have k equals 0, so we're just going to start with k equals 0, so we get x to the 0 because we have that first term is just a constant. And we can go to any degree. So if I wanted the fifth degree Taylor polynomial, it would be this plus x to the fifth over 5 factorial. Sixth degree would be that plus x to the sixth over 6 factorial, and so on. All right. Let's take a look at the natural log of x. So in this case, we're going to go all the way to the sixth degree. We're going to find the sixth degree Taylor polynomial for ln of x. But this time we're not going to do it at x equals 0. We've done the last two we did at x equals 0. We're going to do this one at x equals 1. All right, so we know that it's going to take this general form. A lot of terms in this one. All right, f of a, f prime of a times x minus a, f double prime of a over 2 factorial times x minus a squared, f triple prime of a over 3 factorial times x minus a cubed, all the way up to the sixth derivative over 6 factorial times x minus a to the sixth. All right, so I need lots of derivatives. I need the first 6 derivatives of ln of x. This one takes a little bit of work. It's not quite so nice as e to the x. All right, so I have, here's my first 3 derivatives. 1 over x, negative 1 over x squared, 2 over x cubed. And when I evaluate those at x equals 1, I get these. F of 1 is 0, f prime of 1 is 1, f double prime of 1 is negative 1, f triple prime of 2 is 2. All right, so again, I'm just plugging in. Sorry, this should be, I'll change this in the notes, but that's f triple prime of 1 equals 2. All right, so I'm plugging 1 into this derivative and I'm getting 2. I need the fourth, fifth, and sixth derivatives, so here's the fourth, fifth, and sixth derivatives. When I plug in x equals 1, I get these values for those derivatives at x equals 1. All right, so here I've rewritten negative 6 as negative 3 factorial, 24 is 4 factorial, negative 120 is negative 5 factorial. You can verify those if you like. And so the sixth degree Taylor polynomial looks like this. Now notice here that our derivatives start to look like, well, start to include factorials, right? This third derivative of f at 1 equals 2. That's also 2 factorial, right? 2 times 1 is still just 2. This is the 3 factorial. So whereas with the general Taylor polynomial, we always have the factorials in our denominator. With with ln of x, we also get some factorials in our numerator, which are going to cancel out some of those ones in the denominator. All right, so we have second degree term is always over 2 factorial, third degree term is always over 3 factorial, fourth degree term is always over 4 factorial. And in these numerators, these are where our second derivative, third derivative, fourth derivative, fifth derivative, and sixth derivative start to come in. And for instance, with this last term, 5 factorial over 6, this is 5 times 4 times 3 times 2 times 1. This is 6 times 5 times 4 times 3 times 2 times 1. So the 5 factorial cancels out everything but the 6 itself. So we're left with an expression that no longer has to have factorials in it. They were there in the development, but they're not there in the final analysis, in the final statement. So you can see here that we have alternating signs again because of the way this derivative worked out. Every time we multiplied by a negative coefficient, in essence. So we got these alternating signs. We have x minus 1 terms because we're centering this thing at x equals 1, so it's x minus a. And then we just have 2, 3, 4, 5, 6 as our denominators. Right? So again, we could generalize that and think about what the nth degree Taylor polynomial would look like if we centered it around x minus 1. We could continue this pattern.